Okay, let's consider the noise performance of a double sideband suppressed carrier AM modulation system. So for the modulation system, we start with a message signal, or the modulating signal x of t, into a mixer, which is simply a multiplier, where it's mixed with a carrier signal, a cosine with a particular amplitude AC and a particular carrier frequency f sub c, and the product is the modulated double sideband AM signal. So the double sideband suppressed carrier AM signal is AC x of t times cosine 2 pi fct. This is simply the result of this multiplication. This modulated signal is passed through a noisy medium, so the modulated signal is passed through a medium where noise n of t is added, and the sum of the signal, the modulated signal plus the noise, is applied to a receiver. The first step in the receiving process is a bandpass filter that has a bandwidth given by B with the subscript R for receiver. And the signal that comes out of this bandpass filter will be the modulated signal. See, this filter is designed to isolate the spectrum of this double sideband AM signal, and it passes that through, and it then also passes a portion of the additive noise. It passes that portion of the noise that falls in the bandwidth of this bandpass filter. So now we have a signal, and we have signal plus noise into our demodulator, our detector. So we can investigate the signal power into the demodulator and the noise power into the demodulator. Then we have this detector, and which will be synchronous detection for this form of amplitude modulation. That is then followed by a low-pass filter, which isolates the spectrum of the demodulated signal. And what the signal that comes out of the low-pass filter will be our demodulated signal plus the noise, a portion of the noise signal that makes it through the demodulator as well. So we can look at the signal to noise ratio at the output of the demodulator. Okay, so the signal that is applied to this demodulator into the detector, labeled here as R of t, is going to be the double sideband signal plus the noise that's made it through this bandpass filter. So the double sideband signal is AC x of t times cosine 2 pi fct plus the noise that has been passed through the bandpass filter. And this now want to next look at the signal to noise ratio at the input of the demodulator. For the input signal power, we take the input signal, which is AC x of t times cosine 2 pi fct, square it, so this is the signal squared, and then we're taking the time average, so that's the bar across the top indicates the time average. So if we work this out, we can apply the trig identity to this cosine squared. We would have AC squared, that's a constant squared, then x of t squared, that's the message signal squared, and then that's going to multiply a 1/2 plus 1/2 cosine 2 pi, twice the angle is going to be 2 times f sub c times t, and then this is all time averaged. We can distribute through the cosine squared, and then we'll have two terms, and since we're taking the time average, we found that the time average will be the time average of the two terms individually taken. So this is going to be a 1/2 AC squared x squared of t time averaged plus a 1/2 AC squared x squared of t times the cosine of 2 pi times 2fc times t, all time averaged. The second term has a constant times a positive function, which is multiplying this cosine, which is goes both positive and negative. Well, this is going to, second term is going to time average to 0. That leaves us with the first term. 1/2 is a constant, so its time average is 1/2. AC squared is a constant, so its time average is AC squared. Then we're left with x squared of t time averaged, and this term is simply the power in the message signal. So now we have this expression to give us the signal power into the demodulator. So we have a handle on the signal power that goes into the demodulator. The noise power into the demodulator is simply the noise power that has made it through this bandpass filter. So we are assuming, or we are modeling this noise as white Gaussian noise that is passed through this bandpass filter, and as we have already determined, the noise power that is passed through a bandpass filter is equal to N naught. N naught being the N naught over 2 is the value of the power spectral density of the Gaussian white noise, and we have a bandpass filter with bandwidth B sub r. Okay, so we've already worked out in previous discussions that this is the noise power that will survive through a bandpass filter. For double sideband AM, this receiver bandwidth has to be twice the bandwidth of the message signal, so this is the bandwidth of the double sideband AM signal. So if we plug in 2 times BR, I'm sorry, 2 times B is equal to BR, we get then the noise power into the demodulator is 2 times N naught times B. So this now we can use for the noise power in, and we can form the signal to noise ratio. We have the signal power that was that we just wrote by taking the time average of the signal that goes in the top of the fraction. The noise power goes in the bottom of the fraction, and this now is an expression we can use for the signal to noise ratio. It's expressed in general terms. Did a little algebra to come up with this expression. It involves the amplitude of the carrier, the power of the message signal, the background noise intensity, and also the bandwidth of the bandpass filter. So we've got the signal to noise ratio, or an expression for the signal to noise ratio at the input of the demodulator. We want to see how the demodulator, that is the detector in the low pass filter, what effect that has on the signal to noise ratio. And for double sideband AM, the demodulator takes the form of this synchronous demodulation. We will take our received signal and mix it with a replica of the carrier. I've given this replica an amplitude of 2. It will cancel a 1/2 that will occur later. So that's applied to a mixer. And these amplitude scale factors are not significant when it comes to the signal to noise ratio, because those amplitude scale factors end up multiplying both the signal and the noise, so they cancel in the signal to noise ratio. So the output of this mixer passed through a low pass filter, and then we have our received signal y of t, just simply shown as y of t here. So the signal into the mixer is the double sideband AM signal, AC x of t cosine 2 pi fct, plus the noise that has passed through the bandpass filter, which we can represent as narrowband noise. And we worked out this model for narrowband noise that involves a random amplitude function multiplying an in-phase cosine summed with a random quadrature phase function multiplying the quadrature phase carrier. NC of t and NS of t are random amplitude versions for the in-phase and quadrature components of the noise. The noise is distributed over these two components, one in phase with the carrier, the other 90 degrees with the carrier. And let's consider that the power will be evenly distributed over the in phase component and the quadrature phase component. So NC squared time averaged is going to be equal to NS squared time averaged. That's simply saying that the random noise power is evenly distributed over these two components. Okay, I'm looking to find the total noise power into the detector of the demodulating system. So the noise is modeled as this narrowband noise model, NCT times cosine 2 pi FCT minus NST sine 2 pi FCT. This noise signal will be squared and then time averaged. So when we apply this, we are going to have these terms. We've got a NC squared t cosine squared 2 pi FCT term, and then we've got a cross term which would be minus 2 NCT times NST times cosine 2 pi FCT times the sine of 2 pi FCT. That's the cross term. And then finally plus the final term NS squared of t times the sine squared of 2 pi FCT. Okay, so we've got these three terms from squaring the noise, and then we're going to take a time average of all of that. So for this cosine squared, that's a 1/2 plus 1/2 cosine at twice the angle, and then that's multiplied by NCT. So that's going to give us an NC squared of t over 2 plus an NC squared of t over 2 times the cosine at twice the angle, which is 2 pi times 2 FC times t. Okay, this is from the first term. And for the second term, I need the cosine times a sine. Okay, the next term is a cosine times a sine times 2NC times NS. So we add, and then when we take a cosine times a sine, we get a 1/2, which cancels this 2. Then I'm going to have an NC of t times the NS of t, and then the cosine times the sine gives a sine at twice the angle, and then we get the next term is going to be minus, and then we have an NC of t times an NS of t times the sine of 0, and which is going to be a term that goes to 0. Then we have finally a sine squared, so that's going to be plus squared of t over 2 times a cosine of 0, which goes to 1. Finally, minus ns squared t over 2 times the cosine of twice the angle, 2 pi times 2 FCT. Okay, so these two terms come from the cosine times the sine, these two terms from the sine squared, and then we're taking the time average of all of these terms, so we can take the time average of each term individually, and you see that that the time averaging takes out all of these terms that multiply the cosine. These will all time average to 0, and this sine as well. That will time average to 0, and this term will time average to 0. So we're left with two terms that in the noise power that is applied to the demodulator, and the total noise power as applied to the demodulator is equal to 1/2 NC squared. This is the in phase noise power, plus 1/2 NS squared of T is the quadrature phase, quad phase noise power. So, and this makes sense. We are modeling the random noise as having an in-phase component and a quadrature component, and the total power would be the power in the in-phase component plus the power in the quadrature phase component. That all makes sense. So we've determined that the total noise power into the demodulator is equal to the in-phase noise power plus the quadrature phase noise power. And that these must be equal to each other, which means that NC squared time averaged is equal to NS squared time averaged. This is required because we are stipulating that these two power equations have to be equal to each other, which means that if you the total noise power is going to be equal to 1/2 NC squared time average plus 1/2 NC squared time averaged again. So that makes the total noise power equal to NC squared and time averaged. And we've also already determined that the total noise power is equal to 2 times N naught times B. So if we equate these two together, we can now have a value for NC squared time averaged, which is going to be 2 times N naught times B. And this we can now use in our signal to noise ratios. So we're back now. I'm looking at the signal that is applied to the mixer and then passed through the low pass filter. This signal R of T that is applied to the mixer is the double sideband AM signal. So this is phi double sideband of T is this portion of the signal, and this is the narrowband noise that is passed through the bandpass filter, and this will give us the total where'd my diagram go? There it is. This is the total signal that is now mixed with a replica of the carrier and then passed through the low pass filter. So the demodulated signal, we take the received signal, which is this signal, and we multiply it by the replica of the carrier, and then we low pass filter the result. So the received signal, the double sideband signal plus the narrowband noise, I've expressed here in this bracket. Here we have the double sideband signal, AC x of t cosine 2 pi of CT, plus the next two terms are the narrowband noise. That's all multiplied by this replica of the carrier, and then we're going to low pass filter this result. So we have here a cosine times a cosine term, so that's 2AC x of t cosine squared 2 pi of CT, cosine times a cosine term plus 2 NC of t cosine squared 2 pi FCT plus a cosine times a sine term. So that's minus 2 n sub s of t sine 2 pi FCT times cosine. And now for the cosine squared, we have a 1/2 plus 1/2 cosine at twice the angle, so that gives us 1/2 cancels the 2, and we get AC x of t, and then 1/2 cosine at twice the angle, so that gives us AC x of t times cosine 2 pi FC, 2 pi times 2 FC times t. For this cosine squared, again, 1/2 plus 1/2 times cosine at twice the angle gives an NC of t plus NC times cosine 2 pi 2 FCT, and then the sine times the cosine gives a sine of the difference of the angles minus a sine of the twice the angles. So we have this term NS of t times sine 0, and sine of 0 is 0, so this term is zeroed out. And then we have NS sine 2 pi 2 FC times t, and these are all low-pass filtered. So the low-pass filter takes out this high-frequency cosine. Low-pass filter takes out this high-frequency cosine, and the low-pass filter takes out this high-frequency sine. So the result of the low-pass filtering is the sum of these first two signals. The signal that comes out of the low-pass filter is AC times x of t. Well, this is a replica, scaled replica of the message, and then we have the noise. This is the in phase. Yes, this is the in phase noise. You'll notice that the quadrature phase NS term has been eliminated completely through this synchronous detection, because the synchronous detection retains the in phase component, but since it's at 90 degrees with the quadrature phase component, that part is filtered out or eliminated. The output signal is this replica of the message signal. So we can find the signal power in the output is simply going to be this signal squared and then time averaged. So that's going to be AC squared times x squared of t time averaged. And the output noise is going to be n sub c squared and time averaged. And we've already determined that that's equal to 2 times n naught b, as we saw on a previous page. So the output to signal, the signal to power ratio at the output of the low-pass filter has this. Now we're using this signal power in the top of the fraction, and we use this expression for the noise power in the bottom of the fraction, and this forms an expression for the signal to noise ratio. So that's AC squared over 2 x squared time averaged divided by n naught b. Now we've looked at the signal power n. That was AC squared over 2 times x squared time average. That's this portion of this fraction for the signal to noise ratio. So we can write that the signal to noise ratio at the output is equal to the signal power at the input divided by n naught b. Now let's try to summarize this and come to a conclusion. We've got the signal to noise ratio at the output of the demodulator. The signal to noise ratio at the input of the demodulator, here it is, was given by this expression, AC squared over 4 x squared t time average divided by n naught b. So if we take the expression for the signal to noise ratio at the output and compare that to the signal to noise ratio at the input, compare these two signal to noise ratios, and we get this factor of 2, so that the signal to noise ratio at the output is equal to 2 times the signal to noise ratio at the input. What this says is the signal-to-noise ratio that comes out of the demodulator is larger than the signal-to-noise ratio that goes in. So this demodulator improves the quality of the signal, and that's because the synchronous detection rejects the quadrature noise component. So half of the noise is removed in the demodulation process. So that's good. That improves the quality. Now, to make another comparison, though, we want to compare the signal-to-noise ratio with the double sideband to the signal-to-noise ratio for the baseband system, where we had no modulation at all, which we worked out in a previous study. The signal-to-noise ratio for the baseband signal SN, signal power N divided by N naught B, and this is expressed here, and you can see that they are exactly the same. So the conclusion we can draw from this is that a well-designed, this is the upper limit. It's you can't get any better than this. It can certainly be worse if you had a poorly designed or poorly built double sideband AM system, but a perfectly designed, perfectly built double sideband AM signal, AM modulating demodulation system performs no worse than baseband. It performs exactly the same in terms of signal to noise ratios. Now we'll find that this is not the case for conventional AM transmissions.